And so then let's go in and let's take a look at kind of a simple little example to show you how this works. And again, we can do kind of like multiple directions, and so that can be kind of useful. We'll start off with something easy that isn't very challenging, and I'll probably reference it again later in the lecture on Tuesday of next week. So about train cars. And so the reason that these are pretty nice to discuss is because they have these little couplers that'll allow them to hook together. So we'll start off with our two train cars that are separate. Then we're going to have a collision where they interact with one another. And what you'll find is that the net force over the system of both train cars will be zero, because we're going to rely upon the fact that the forces will come as third law pairs. So you're going to have a force on the second train car by the first, and then you have a force going back on the first train car by the second. And while I don't know what those forces look like, little to big to little kind of things, they're going to interact with one another, and they're going to be third law pairs, so that over the system, they will sum to zero. So that's going to be a very nice feature. And in fact, as a general rule, when they talk about conservation of linear momentum, they almost always relate it into Newton's third law. Okay. So in this example, what I'm going to have is I'm going to have two train cars that are going to interact with one another, and they're going to hook together and then move off together like this. So let's go in and state that I don't know, let's make our first train car, 10,000 kilograms, because 10 kilograms is ridiculously way too small. Do you want the second train car to be the same or different? Different? Okay, I agree. Let's make it heavier. We'll make it 15,000 kilograms. And we'll have the first one heading in at, I don't know, 5 meters per second. And we'll say that the second train car was at rest. Then this little squiggle that I put in here, this is to indicate the collision. And what's happening in the collision are that there are forces acting between the two train cars that I don't even know what they are. It's the little to big to little kind of thing that I don't know what it looks like. I can't write down a formula. I got nothing, but what we're going to find is, because we have this conservation principle, then I can jump from the beginning and then jump to the very end and figure out what happens at the end, even though I don't know what happened in the middle. It's a very interesting type of thing. This is why this technique is so powerful. And so then we're going to assume that they're going to hook together, which is, again, why we generally like to do the little train cars. So mass 1 plus mass 2, this would then be 10 plus 15. This would be, what, 25,000 kilograms. And what we're going to work on is, well, how fast are the train cars going to move off after they, couple together. Okay. And so what we're going to find is that if we look at the forces, then, we have the y direction. We would have gravity's down and normal forces up, and then gravity down and normal force up, but yet there's no motion in the y direction. It's like they popped up into the air or like dropped down through the ground or something. So I don't care about the y. I do care about the x, this horizontal direction, which I'm going to call x. And so you get that the first car is going to act on the second car, and then the second car is going to act back on the first car. Those are going to be third law pairs. And even though I don't know how to write down the force at all, I can figure out how fast we're going when we're done. Okay. This is kind of like, reading the first chapter in the mystery novel and then reading the last chapter, and you know how it ends. So it's good times. So we'll go in. I'm going to pick out that. We'll pick that, to the right will be the positive direction. I'll call it my positive x direction. So we'll code this into our coordinate system. Don't need to worry about this. These are scalars. And then we can go in and write down our conservation of momentum. But what we would state is that since the average net force on our system in the x direction is 0, then we will have a conservation of momentum in the x direction. So this is, again, first one exerted a force to the right on the second exerted a force backwards on the first. And what you get is that the first one causes a forward acceleration on the second, causing it to speed up to go from rest to moving. The second one causes a backwards acceleration on the first, causing it to slow down. And even though the force is not constant, the acceleration is not constant, I can still figure out how fast we're going at the end. And so since we have this condition, and our momentum in the x direction is going to be conserved. Okay. Now, when I write down my terms, I wrote them out kind of generically here, one term for each object. But when I write it down like this, where they hook together, then I kind of like to write it so that it looks like this instead. So I'm going to write down that this is m1 times my v1x plus our m2 times v2x. And then when they stick together, then I usually write this as m1 plus m2 times v prime x. And since it's a shared velocity between each car, then I don't need a 1 and a 2 on it. I could put 1 and 2 on it, I guess, if you wanted to, but I generally don't put any numbers on them. And so in my, so in some sense, I think of this as like one term, and then these as two terms. I think it looks like the picture. This one here plus that one there equals this one there. And it's ridiculous because if you distribute it, you go back to two terms, but I don't know, in my brain, I go, it's a mass times one velocity. That's one term, one composite object kind of thing. I don't know. All right, so then let's go in and show you how to figure out this velocity at the end. So the mass of car one was our, 10,000 kilograms. My velocity here is that plus 5 meters per second. The second train car was at rest, so if it's not moving, there's no momentum. The combined mass of the two train cars is our 25,000 kilograms. And since this unknown v goes in the positive direction, I'll write it as plus v prime. Okay, so to the right, v prime, so a direction and magnitude. And then to solve for that, we just go in and divide both sides. And so then our v prime turns out to be how much? 2. Thank you. Now, let's talk about what this means. So this is one of those things that I want to have in our discussion, okay? And so since my answer came out positive, then technically the way that we discuss this is that since I coded the directions when I coded the equations, I put in the directions, getting a positive answer for the magnitude, because this is the magnitude and direction. That means that the direction I picked when I coded the equation was correct. Okay, so this is really how we should be talking about our solutions to vector equations. And so this means that I, pick the correct direction. And so back here, when I picked directions, I said that it was going to go, to the right. And so therefore it goes to the right. So then my answer is that it is 2 meters per second to the right.